class. Welcome to the next section, chapter 10.4, Physics and Engineering Applications. Today we're going to talk about moments and center of mass. Let's consider two masses, which we'll call M1 and M2. And let's say that these masses are attached by a rod. The distance between the masses determines the balance point of the rod. So remember here that these two masses can be the same mass or they can be different. So think about two different weights that are separated by a mass, and the balance point is somewhere in the middle, right? The distance between the balance point and the respective masses is D1 and D2. So if we have the balance point, the distance from the balance point to the first mass is D1, and the distance from the balance point to the second mass is D2. So if we draw a picture, we have our first weight M1. Let's say M2 is larger. It's really arbitrary. They can be the same size. And so they're connected to a rod, right? And so the balance point is somewhere between these on this rod, okay? And so we would call the distance from the first mass to the balance point D1, and the distance from the balance point to the second mass is a distance of D2, okay? So we can then say that the balance point is when the mass times the distance is equal to this mass times this distance, okay? So that's our equality here. Right, so this should make sense even though this is not to scale. I have a large weight and a small distance, small weight and a large distance. Those two products should be equal to find the balancing point. Again, and that should make sense because it's the balance point, right? It's the point where two things are equal, right? So say we create a number line, and we say that this is in the x direction in order to help us kind of figure out some of the calculations that we want to do. Okay, we can say that M1 lies at the point x1 and M2 lies at a point that we'll call x2. Then the balance point we'll call x bar. Okay, so the distance for D1 is the balance point minus the x value location for M1. So x bar, the balance point, minus M1's location. The distance 2 is the same thing. It's going to be the distance of M2 minus the balancing point, right? So x2 minus the uh, balance point. So if we look at this on a number line, if I set this at somewhere at 0, right? We move on for some distance until we hit M1. We say that M1 is a distance of x1 from 0, right? X2 is the second distance for the second mass, and the balance point is somewhere between those two values. So again, this first distance is x bar minus x1. So this whole distance minus this amount, right? And this distance is all of x2, and then subtract x bar, right? The distance from 0 to x bar, and you get the distance for uh, D2, the distance from the balance point to the second mass. So we have M1 times D1 is M2 times D2. We can make some substitutions now for D1 and D2. D1, remember, is x bar minus x1. D2 is x2 minus x bar. Okay, so we make those substitutions, and so M1 times x bar minus x1 is the same as M2, and then the distance between the balance point and the second mass. So we can start to do some math here, right? So I distribute this M1 across, and I distribute this M2 across this parentheses. From here, I can start to get the x bars on one side. So I'll add M2 x bar to both sides, and I will add M1 x1 to both sides. So I have all of the x bar stuff on one side. From here, I can factor out the common x bar term, okay? And then divide by the M1 plus M2. And now we have a formula for that balance point. Okay, so that balance point is going to be the first mass times its distance from 0. The second mass times its distance from 0, the sum of those, divided by the sum of the masses, right? Each of these mi x i's is called a moment, right? So the mass times its position is called a moment of the system. If there are multiple moments, many masses, right, then x bar turns into this formula. It's the exact same formula. The denominator, I'm adding up all of the masses, okay, and in the numerator, I'm adding all of the moments, right? So that balance point is the sum of the moments divided by the sum of the masses, okay? So we call this big M over little m. Big M is the moment of the system about the origin, and little m is the total mass of the system. All right, so in a two-dimensional system, we have to consider the balancing point about the y-axis as well, which we call the moment about y, so large M, uh, subscript y, and about the x-axis, which is m about x, okay, the moment about the x-axis. So the moment about the y-axis, right, is what we looked at just a second ago. Okay, so again, if we kind of come back to what's going on here, if we think about the y-axis going up and down, we're looking at the moments as they revolve around the y-axis, right? So the y-axis is the center, right? Because so again here about the origin. So if we're looking about uh, the y-axis. So we're considering the y-axis as our center. So we're looking at all the things along all the moments in the x direction, right? The moment along the x-axis is considering the x-axis as the center. So we're looking at all the things up and down, right? Because the x-axis is what we're looking at the moments about. So x bar is, as we saw before, is the sum, is the moments of about y divided by the total mass of the system. So the moments about y divided by the mass of the system. And y bar is the moments about the x-axis divided by the total sum. So here we're looking at the ups and downs. I'm sorry, yeah, the ups and downs, right? Because we're looking at the x-axis as our center. So we're looking at how things are above and how things are below. For the x-axis, it's the opposite, but rotated 90 degrees, right? So the y-axis is our middle. So we're looking at how things are scattered about to the left and to the right of that. Okay. So x bar is the moment about y over m, and y bar is the moment about x over m, right? The total mass. So then the center of mass of the system is x bar and y bar. Okay, so now in a two-dimensional system, any two-dimensional object, we can find the center of mass by looking at these sums. So let's do an example. Okay, let's find the moment m of the system about the origin, right? So the total moment, and the center of mass, x bar. Okay. So here we're just along x, right? So very similar to what we did at the beginning here, okay, with actual values. And so in this example, we have three moments, okay? We have M1, M2, and M3, three different masses, and they are spread out along the x-axis, right? So somewhere here would be the y-axis. So we're just kind of looking at how these are spread out relative to the y-axis, which is why we call it the moment about y. So M1 has a distance of -3 from 0 with a mass of 12. M2 is a mass of 15 at 2, and mass 3 is a mass of 20 about 8. As you can see, there's no units here, which is nice for right now, but we could definitely be working with units in the future. So the moment of the system, M, uh, is going to be the sum of MIXI. So we're going to have 12 times -3 plus 2 times 15 plus 8 times 20, right? So that's the moment of the system about the origin. So that's going to give us 154. Then we're going to take the sum of the masses, right? Little m. So for x bar, we're going to get 12 plus 15 plus 20. Okay, so we already have this m on top. So I need the sum of the masses. Remember, big M here is 154. Okay, the sum of the masses is this 12 plus 15 plus 20. Okay, 12 plus 15 plus 20. And so for this, we just add them up. We get 154 over 47. and that's it. So that's our, we found the moment M of the system about the origin, which is this 154. So just the sum of the masses. And then we found the X bar location, which is 157 over 47. We could plug this into a calculator to get more technical, but this is somewhere around 3, right? Somewhere around, somewhere around 3. So somewhere about here would be where it is. So now we want to find the moments about X, about Y, and the center of mass of the system for M1 having a mass of 5 at the point -4, 2. Mass 2 is 4 at 0, 5. Mass 3 is 3 at 3, 2. Mass 4 is 6 at 1, -2. So in order to find mx, I'll go back to the formula. A good way to remember this is you're doing the opposite, right? So for the moment about x, I'm looking at the y's. The moment about y, I'm looking at the x's. So for the moments about x, I'm going to multiply my mass times my y values and sum them together, right? So the moment about x is the sum of my masses times their respective y values. So I'm going to have 5 times 2 plus 4 times 5 plus 3 times 2 plus 6 times -2. Okay, so that's 10, 20, right? So that's already 30, and then 6 and -12, uh, so -6 basically. Okay, so 24, so 30, and then this is -6, so 24. The moments about y is going to be the same thing, but I'm going to be multiplying times the x values. Okay, so the moments about y is m times their x values. So 5 times -4, 4 times 0, 3 times 3, and 6 times 1. So this is -20, 0, 9, and okay. So we add these together, and we will get -5. The sum of the masses is this 5 plus 4 plus 3 plus 6. Okay, so here we're going to get 18. So we got the 4 and the 6 is 10, 5 and the 3 is 8. So we got 18. And now we have the information to find the rest of the center of mass of the system. We just take these moments, right, about x and the moments about y, and we divide them by the sum of the masses. So for the first one, it'll be 24 divided by 18, okay, for about y. And then about x is going to be 5 divided by 18, right? So mass about y is actually our x value, right? Remember how this works. X bar is mass about y over m. Y bar is mass about x over m. Okay, so mass about y divided by the sum of these masses is the x value, the x bar value, and then this divided by the sum of the masses is the y bar value. There you go. -5 over 18, 24 over 18, and we can simplify this 24 over 18 to 4/3, right? So the center of mass is at -5 over 18 and 4 over 3. If we have a continuous case, right? So this is discrete values. This is a point. This is a mass at a point, right? A mass at a point, a mass at a point, a mass at a point. Let's say we had functions, continuous functions instead, right? Uh, we would call these thin plates, and which we call laminar, and we would then use an integral instead of these stuff. Okay, of uniform density, which we call rho. That can be modeled by on an edge by a function f of x. The center of mass is of a solid is called the centroid. Okay. If we break the curve f of x into approximating intervals or bars, as we generally do, we can take the sum of the center of these bars as the number of bars increase, as n goes to infinity. We will get the moment about y. which is the limit as n goes into infinity, basically the number of bars, um, where each sum is the density of that bar times the x value average and the y value average, right? The central height. Okay, so basically what we're doing is for each bar, we're taking into consideration what its mass is, right? And then we're finding that midpoint times delta x. So here rho is the density of each bar, x bar I is the x value for the midpoint in each bar, which is very easy to find. And f of x bar sub I is the area of each bar times delta x, right? So the length times the height. So here we have our curve f of x. This is the center of the ith bar, and that centroid is right in the center, x-wise, okay? Height-wise, it should be halfway of the height for uh, the function evaluated at this x bar, okay? Which should make sense because it's the center of the bar, right? So it's halfway in the middle in x, halfway in the middle of the function height. So that's the moment about y. We can take that limit of the sum and just write it as an integral from a to b from the beginning of our interest point to the end. Rho, the density times our x value times the function height. Okay. For the moment about x, we have something very similar, right? So remember, this is for x values. This would be for y values. That's why we have the 1/2 f of x bar. Here we're just looking at the x value times function times the mass, right? So 1/2 f of x bar is the y value for the midpoint in each bar. Therefore, the moment about x is the integral from a to b, 1/2 times rho times our function squared, okay? 1/2 times our function for the y value, and then here for the area of our bar. F of x bar times delta x is the area of each bar, and then this is the location of the midpoint. Okay. And lastly, our mass for the system, the mass of the plate, is going to be rho times the area, and the area can be found as the integral from a to b of our function, right? So the rho is still here because it's the mass over that function. Okay. So leave this here for a second. So we have our function for m about the mass about the moments about y, the moments about x, and our mass in general. Okay. Therefore, x bar is the moments about y over the mass. So that's two integrals, right? Rho x f of x over the integral rho of our function. Remember here, this rho, this mass is a constant. This is a constant term. X and f of x are what we're evaluating our integral in, right? The differential is an x. Rho is just a constant. So I can pull this rho out and I can pull this rho out, and guess what? Numerator, denominator, I can cancel it out. Okay. So I'm not canceling out inside of the function. I'm pulling these out first and using the laws of integration to say that, I can cancel out something in the numerator and denominator if it's a constant multiple of an integral. So that is how I find my x bar. My y bar is very, very similar. It's the moment about x divided by the mass of the system. So that's two integrals, both having rho in the numerator and denominator. I get to pull those out and cancel them. This 1/2, I can move to the denominator as a 2. You don't have to, but for me, it's easier to do that when I do my calculations. And so then that is the y bar value of our system. Okay, so if our laminar is bounded by two curves, f of x being the larger curve, possibly equal, um, then x bar is going to be very, very similar, right? It's going to be x times the difference between f of x and g of x divided by the integral of the difference between f of x and g of x, right? So the difference of the two curves, y is going to be the same thing, y bar, okay? I'm going to square f, and I'm going to subtract the g function squared, take that integral, and for the denominator, it'll be the same thing, it's the mass. Okay. So let's go ahead and do an example, right? Um, Formulas are great, but if we don't have an example, then it's not as clear what we need to do. So let's find the centroid of the region R between y equals x to the fourth power and y equals x to the sixth over the interval from 0 to 1, bounds included. Okay. So in order to find the centroid, I need the moments about y, I need the moments about x, and I need the mass of the system so that I can find x bar and y bar, which is the centroid of the region R. Okay. Note that between 0 and 1, the smaller function is actually larger in value. Okay. And that's because we're between 0 and 1. So if I take something like 0.5 and I multiply it times itself 4 times, that's a larger value than if I multiply it times itself 6 times because we're in decimals, right? So the more times I multiply a decimal times itself, the smaller value I get out. Okay, so x to the fourth is actually the larger valued function over this interval. So your interval of existence is important, right? Otherwise, you could be doing it incorrectly. So x to the fourth is my larger function, and x to the sixth is my smaller function. So I need to use this, well, we have two functions here, so we'll be using these two functions, okay? I'm not just doing it over one function, right? From one function to the x-axis or the y-axis. We're between two functions, so we'll be using these two formulas here. So for the first one, for x bar, to find the moment about y, I take x and I multiply it times the difference of these two functions, where this is my f of x and this is my g of x. Okay. For y bar, I'll square this one, I'll square this one, and I'll find the difference, and then I will go ahead and find the integral. Okay. So let's go ahead and do this. So we're just plugging everything in. X fourth was my f function. X to the sixth was my g function. Um, I'm going to multiply this x across. Okay, x to the fifth minus x to the seventh. There's nothing special to do here. We don't need a factor, pull out highest common factor or anything like that. It's a standard polynomial. So we're just going to integrate both, right? So this is going to turn into 1 over 6, x to the sixth. This will turn into 1 over 8, x to the eighth. Okay, we'll evaluate that from 1 to 0. Very clear here, when I plug in 0, this goes to 0. When I plug in 1 for both of these, I just get the 1/6 minus 1/8. Okay, so your common denominator here is 24. So this turns into 3 over 24, and this is 4 over 24. So that's just 1 over 24. Okay, so that's my moment about y. Mx is the same thing. I'm just gonna plug in x to the fourth and square it, plug in x to the sixth, my g function, square it, and then subtract them. Again, I don't actually have to do anything here. It's just a polynomial. So this turns into 1/9, x to the ninth, 1 over 13, x to the 13th, with the 1/2 in front. Same thing, when I plug in 0, these both go to 0. When I plug in 1, it's just 1 over 9th minus 1 over 13th, okay, with the 1/2 here. Here, in order to get the common denominator, I multiply this top and bottom by 13, this top and bottom by 9. Okay. Common denominator in that case is 117. The difference here is 4, but I'm dividing that by 2, so that's 2 over 117. Okay. So I got my moment about y, my moment about x, and now I need the mass of the system. So that is the integral. So again, notice here for the moment of x, I incorporated the 1/2, mainly because uh, if I did the 2 on the bottom, it's kind of unnecessary because I could just use this value twice. So I'm using a slightly different formula here, um, but that shouldn't be confusing to you. It's really only because I could just find this. I could find this here with the 1/2 in front, and then I can find the mass of the system and then just divide both of those values, right? Like we've been doing. So you have a little variation that you can do here. So my mass of the system is just the subtraction of both of those. So we'll do the same thing. 1/5 x to the fifth, 1 over 7 x to the seventh. Evaluate that from 1 and 0. So this is just 1/5 minus 1/7. Make the common denominator. So that'll be a 35 and 7 minus 5 on top. So that should be 2 over 35. Okay. And so then to find the centroid, it's just the moment about y over that value we just found for the mass, and the moment about x divided by the mass of 235. So for x bar, 1 over 24 divided by 2 over 35. Remember, you multiply this and flip the reciprocal. So that will be 35 over 48. And y bar will be the same thing, 2 over 117 and 2 over 35. Make sure here, y, this is x, so that's the y value. Okay, and so then when we do this, it'll be 35 over 117, and that is my centroid. Okay, so my centroid is 35 over 48, 35 over 117. So now this brings us to the theorem of Pappus. Let R, fancy R here, be a plane region, meaning that it is a region in a two-dimensional space, right? It's a two-dimensional space in your plane. Actually, it could be a plane inside of a three-dimensional space, right? It's just a plane, okay? That lies entirely on one side of a line, which we will call L, okay, which is in the plane as well. If R, this plane region, is rotated in three space about that line that R lies above, then the volume of the resulting solid, okay, so remember, you rotate a two-dimensional object in three dimensions, you get a solid, right? And the volume of that solid is that area A of R, the plane region, and the distance traveled by the centroid of that solid. Okay, so example, find the volume of the solid attained by rotating the region enclosed by y equals x cubed, y equals 0, and x equals 1 about the line x equals 2. Okay, this is the same problem that we have solved a few times in this class using different methods. We solved this in chapter 8.2, the volumes lecture, um, by using the ring method. Okay, and we solved it in chapter 8.3 by using cylindrical shells. So we've done this problem twice already. So I suggest you kind of go back and look at it now just to like refresh, but we're going to do it all over again. But we did do this problem twice, so this is the third time. So hopefully you remember this from the lectures, but I have this curve. This is the area, right? This is my region R, and I'm rotating it about the line x equals 2. And this is just the other projection into the xy plane here, right? But I'm going to get this sort of um, cylindrical object when I rotate it, right? So the area of this region R, again, the plane region, so the plane region R is this shaded in region right here. In order to do that, I'm just finding the area under x cubed, right? It's a very simple thing to do, okay? It's just x cubed from 0 to 1, okay? That's the area. So we know this is going to be 1/4, x to the fourth, evaluated at 1 and 0, so that's just 1/4. Okay, very, very easy area to find. Now I have to find the centroid, right? So I find the area, and I find the centroid, and here, okay. So if R is rotated about the line, L, then the volume of the resulting solid is the area of R and the distance traveled by the centroid of R. So I got to find the centroid and find the distance it travels by being rotated about this center. Okay, so I got to find the centroid. X bar is x times the function, so x to the fourth times the area, which I just found is 1/4. So this is just going to be 1/5. This is very easy to find. 1/5 over 1/4, which is 4 over 5. Okay. Y bar is going to be very similar, right? So remember, I'm squaring this function, x cubed. Okay. Divided by 2 over this denominator. We already know that this is 1/4 times 2. This is going to be 1/7. Okay. So when I can simplify this to 1/2, and then when I flip it, it's 2 over 7. Okay. Very, very easy. You could do this without doing any actual calculations, right? Mentally, at this point, you should be able to look at it and be like, oh, yeah, okay, this is easy, especially since it's from 0 to 1. So now I have my centroid, right? My centroid is 4 over 5 for the x and 2 over 7 for the y bar. The radius of the circle that's made by the centroid is 1 minus x bar plus 1, right? So remember, the centroid is somewhere here. So I have a radius of 1 minimum, and then whatever that distance is to the centroid in the x value. Okay. So the radius of the circle is going to be, I have this plus 1, and then 1 minus x bar. Okay, so this plus 1 is coming from this distance here, because it's from 1 to 2. The distance to the centroid, right, is my x bar value. So I can say that it's 1 minus my x bar value, right, because it's in here somewhere. So the distance up to this is x bar. So 1 minus x bar is the same deal. So 1 minus x bar. So the radius for the centroid then turns into 2 minus x bar, or 2 minus 4/5, which is 6/5. Okay. The volume is the area of that region, which we know is 1/4. 2 pi times the radius created by the centroid, which is 6/5. So area is 1/4. 2 pi, and the radius caused by the centroid is 6/5. Okay, again, the reason is because the radius starts from the center here, not here, right? So the x bar is somewhere here, but the radius formed is this distance left over, so 1 minus however much I move in, plus this extra 1. Okay, and that is where we get 1 minus the x bar plus that 1 because it starts at 2. So when I multiply this all across, I get 3/5 pi, okay, which matches our answer from 8.2 and 8.3, but is much, much less work than both of those problems. Okay. So again, I suggest you go back and look at 8.2, the end of 8.2, end of 8.3, look at this problem, and then just see how much easier this was to do. Okay. Thanks, guys. I'll see you on the next video.